I want to share something else with you. I don't know if it's going to be something that we want to put in the video or not. I'll leave it up to you.
Secret.
But it's pretty exciting. And I'm finally, in fact, I rushed to get it filed, get the patent filed yesterday.
Patent?
Yeah, get the patent. Wow. Got the patent filed yesterday. So now I can talk with you about it.
So we could potentially have a big reveal of a new patented technology or device later in the video.
That's right. I mean, yeah.
I don't know how I could not use, as a YouTube creator, I don't know how I could pass up the opportunity to tease that and then pay it off later in the video. So I'm sure we will.
Yeah, okay. That sounds great.
Okay, let's introduce you for the people who don't immediately recognize your face. You are Chris Rosser. You are, if I remember correctly, an aerothermal engineer by trade?
That by training, yeah.
Yeah, you corrected me. I called you an aerospace engineer once, and you were like, no. And you told me an aerothermal engineer is an expert in everything involved in designing a jet engine.
That's it. Basically, in really simple terms, it's fluid mechanics, fluid dynamics, combustion mechanics, turbo machinery design, all of that stuff. That's what I studied. I didn't actually end up going and doing that for a job. I went into product engineering as a consultant for lots of different companies, and now I work for a couple of startups and also do this drone thing as well. Yeah. Which is becoming a bigger and bigger part of my life.
And it was exciting to me when you first started doing drone things, because the drone industry is full of a lot of people who have very little training in engineering and who are excited about drones and are smart people, and they do their best to figure things out, and they do a good job by and large. But it was very exciting to me to see someone with actual engineering training start applying some of that to drones, doing resonance analysis, finite element analysis, and so on. You started designing a frame, right?
Yeah.
And today you're here to talk about how you've applied your skills and knowledge to motors.
A motor.
Yeah.
Yep. This motor, in fact.
Oh. And I will say, for the people who know me, they know that I am famously unimpressed with motors, and they might wonder why the hell I'm talking to you, other than the fact that, well, I'm always excited to sit down and talk to you because it's always really educational. But and I'll phrase my complaint, which is that most drone motors are pretty much the same. There's very little innovation. There's very little differentiation between them. Like maybe one of them will use a different aluminum alloy, or one of them will use a higher quality bearing. But for the most part, they're all the same. And I think you would agree with that statement.
Yeah. So I would definitely agree that in many ways, all of the motors that we have in FPV are very, very similar. They use the same materials. They have pretty much the same construction. And the kind of really interesting and innovative features that come out, like putting an O-ring on top of the top bearing, has now proliferated out, and now pretty much all motors, include that feature. So in construction, they're really, really similar. And as I guess you will be aware, and probably a lot of people watching this will also be aware, I've tested a lot of different FPV motors, and I've focused on like 5-inch motors particularly, and I've tested over 50 different 5-inch motors now, like all different manufacturers and KVs and all of that. And what I was interested to find is that despite the fact that all of the motors are the same size, pretty much, they use the same materials, they all use pretty much the same strength magnets, all of that kind of stuff, there's more variation in performance of those motors in scientific, repeatable thrust stand testing than I certainly expected.
If you had to put a percent on it, from like the sort of lowest to the highest, what percent difference have you seen in your testing roughly?
Like it could be anywhere from 10 to as much as 30%.
That's big. 10%, maybe not. Really 30%, a lot.
And it's also not like we have a whole heap of motors clustered all together at the top, and then some lower down. It's like it's pretty spaced out. It's even across all of that.
Interesting.
And when I looked at that data, the first thing that jumped out at me is that this makes me think that we haven't optimized this system. Like if you'd have fully optimized the system, you would expect all the motors to perform very similarly, all clustered tightly together, all, you know, at the top end of the performance band, because everyone's optimized and there's nothing more to be done here. We're at the limit of what we can do with the materials that we have and the construction that we're using. And when I saw that that wasn't the case, that really spurred me to actually really try and get into, well, is anyone optimizing? Like really optimizing? And if not, can we magnetically optimize the motor design?
Yeah, and what you've done with this motor is not just tried to optimize the existing design principles, right? Because I think you've seen motors, like I know that RC and Power is one of your favorite motors. They do very, very well in your testing. And you might argue that RC and Power is in some ways the sort of culmination of the current generation of design philosophy. Yeah. But you've not just optimized the current generation, you've actually introduced some new features and new design elements into your motor.
Yeah, so let me kind of take you through the process that I went through. The first thing is the same as what I did with the frames, and it's kind of the approach that I take to a lot of engineering problems, is I tried to model this system. And there is a motor simulation tool produced by MIT that does finite element simulations of motors. Same as, and it does like a magnetic simulation of the motor, and it can predict things like the kV, the torque, the efficiency, the maximum power, all of these things. And it's used a lot actually to design EV motors for electric vehicles.
Sure.
It's not really used very much to design drone motors, at least as far as I know. But I had this wealth of data from over the 50 motors that I tested, all different geometries. And I was actually able to kind of tune this tool and get the parameters of the materials right and the geometry right, so that this simulation tool would very accurately predict the performance of different motor designs.
Sorry to interrupt you, but are you saying that you cross-checked the tool against your actual bench results to sort of calibrate it and dial it in, so you knew that you could trust its predictions?
Yeah. So in engineering, this is called digital twinning. And the goal is to make a model that accurately reflects reality, a digital twin. And then rather than testing the real thing, you can test the digital twin, and you can be confident that how the twin performs will reflect how the real thing performs. So that's the goal. So I had all this data from all these motors, and that meant that I was able to calibrate this model, tune it up, and make a digital twin for a 5-inch drone motor. And it was pretty good. I mean, we're talking within, a few percent of the real bench test. And that tool really gives more ability, more capability to the designer, because if I wanted to test a new motor, I would have to go and get a manufacturer to make me a sample. That would take about a month. I'd get the motor back. I'd test it on my bench. That would take half a day. You get the process. Right. I can tell you, or I can predict how a motor design will perform in about 30 seconds.
Well, and I think it's worth reiterating that point a little bit. Like if you look at, and I'm going to bring up, I worry that by bringing up Bob Ruge, people will think I'm trying to start shit between you guys, and I'm not. But if you look at what he's done in the past, his approach to designing motors is that he has a manufacturer make him a zillion prototypes.
Yeah, like 10 different prototypes.
And they'll send him tiny little iterations, different magnets, different size, and he flies them all.
Yeah.
And that is, in some sense, like it's good because he's actually flying them. But on the other hand, it's incredibly inefficient in terms of time and materials. And it means that it takes a while to figure out what you want out of the motor versus just simulating it on the bench.
Absolutely. So you're simulating it, in this tool in the computer. Yeah. So I could simulate a motor design in 30 seconds and tell you how it was going to perform, right? And that matched the data. Well, so I wanted to take it to the next level, and so I wrote an optimization tool to wrap this simulator. So it would take all all of the different geometric parameters of the motor, the magnet thickness, the height, the flux ring thickness, the stator diameter, the air gap, every geometric parameter that you could think of, the overhang of the magnet on the stator, all of this type of stuff. And it used an optimization algorithm called Nelder-Mead, which is sometimes used for hyperparameter optimization for AI models. Mm-hmm. And the simulator just iterates and tries to find the best combination of geometry.
Right.
And you could do this manually. You could manually test each of them.
Right.
But as we know, you can only sort of test maybe 10 different designs in anything like a reasonable time.
Right.
I ran this tool for over 20,000 iterations.
Wow.
So, we've gone from, testing maybe 2 or 3 designs in a normal case to testing maybe 10 designs or even more if you're Bob to 20,000.
And what's interesting about this approach is that when you as a motor designer go to a motor manufacturer and you say, I want to design a new motor, you have in your head the parameters, like you think, okay, I'm going to use these magnets. Maybe they're going to be this big. The motor size is going to be this big. You have some preconceived notions about what you're willing to try because the manufacturer is going to have to make you samples. And there are some just crazy things that you might not think of as even being worth trying. But of course, the advantage of what you're doing is that the computer can just try everything and wind up with some crazy things about your motor that no one's ever done before.
Yeah, and it turns out that the kind of the optimum design has some very different approaches in it. I think they seem quite different to me, but I think in some ways they can seem quite subtle as well. So, for example, there's been a kind of push to use larger, thicker magnets in FPV motors to get more torque and more power. And that works. And there's also been a push to try and reduce the weight of the motor. And one of the ways that's done is by reducing the thickness of the steel flux ring that goes around the magnets because it's heavy and you can save a lot of weight that way. What my tool found was that thinner magnets and a thicker flux ring produces better performance, more torque, more power, more efficiency for the same weight.
Because there's a saturation point. You explained this to me in a previous conversation, and there needs to be a balance between the magnetic strength of the magnets and the size or weight of the flux ring. Exactly. And with too small of a flux ring, it saturates and the motor can't make any more power, and the additional sort of strength of the magnets is just wasted.
Yeah.
Is that accurate?
Exactly. There's a really nice analogy, which is the electrical analogy. If you think of the magnet like a battery, and you think of the flux ring like a wire, like an electrical wire, you could have a really powerful battery, really high voltage battery. But if your wire isn't thick enough, it just can't carry the current. Right. There's just too much resistance. And so all of that power that you've got in the battery is being wasted because your wires are too thin. And the same is true in motors. You have a magnet that's really strong, really powerful. You don't have enough flux ring. The field can't all fit in that flux ring. Right. It gets oversaturated, and the field kind of bursts out of the motor. And you can actually kind of see this really obviously if you take a steel object and you hold it next to the motor, and if it sticks really hard, right, that's evidence that that there is magnetic field escaping the flux ring.
And that's resulting, I suppose, in a loss of efficiency, because you want all the magnetic flux from the magnets to be sort of contained in the motor and used to make the motor spin.
Yeah, any field that escapes the bell of the motor is field that you could be using to increase the flux in the air gap and therefore get more torque and more power.
So one of the things you did that's unique to this motor is find the optimum balance of the magnet thickness to the flux ring. The other thing you did, I don't know if I'm introducing it too early in the interview, but I think it's really cool, is you actually removed part of the stator core. Yeah.
So that's another thing. I have to be clear that I've seen another motor that does that, but it really helps with the power to weight ratio.
And I think it's going to surprise people because the common sort of way of thinking is that you want to really get a lot of those laminated layers of, what is it, metal?
Silicon steel.
Silicon steel in the core, because that sort of allows you to get more magnetic flux density and makes the motor more powerful.
It is exactly the same as what's going on in the flux ring. So you need to make sure you've got enough steel there to transmit the magnetic flux around the circuit. But there's no benefit to having more than you need. And there is a big penalty to having less than you need.
Okay.
Because again, it's that battery and wire analogy. Again, you know, if you don't have enough silicon steel in the stator, you're restricting the flux. And so you're not getting as much flux as you would ideally get. It turns out that it's quite good to make the motor core slightly hollow, because you can achieve a certain amount of flux between the rotor and the stator. That turns into torque by multiplying that by the diameter of the motor and the area of the air gap. And if you make the motor bigger, you get more area.
Sure.
So making the motor a bit bigger gives you more area, gives you more torque and power.
Right.
But if you then fill up all the internal volume with metal, it adds quite a lot of weight. So if you fill up some of that internal volume with air, you can get a benefit there.
What you're saying is that you've made it bigger to increase the surface area, the mating surface of the air gap, which gives you more torque. But then the volume of the motor, it gives you more metal than you really need to balance to this field, to the magnets. And so you were like, well, let's just put air there and save the weight. So what we've got here then, to recap, is we have a motor that is light, powerful, and efficient, and has been optimized to kind of be the best balance of those three things. Are you ready to talk specs for people? Okay, well, tell me how much thrust does it make? What's its efficiency? How does it compare?
Sure. So I can give you some specs. So on my standard test prop, which is a 5x4.5x3, it'll make over 2 kilos of thrust.
How does that compare to like a T-motor F60 or an RCM Power Smooks motor?
Yeah. So if you give me a second, I'll pull up the actual results. So max thrust, 1,990 grams. So it's delivering more thrust than I think any other motor that I've ever tested.
The chart certainly seems to show that.
Yeah. The efficiency is 81%, which is putting it at the very, very top.
So it is simultaneously the most powerful and the most efficient motor you've ever tested.
That is correct, yeah.
Usually those two things are in opposition to each other. More powerful motors are less efficient.
Direct opposition, yeah.
Okay.
Usually you cannot achieve, usually if you want to make a motor of a given design more powerful, it will always become less efficient and there is nothing you can do.
Okay. Now you're going to tell me it's also the lightest.
It is not the lightest. It weighs almost exactly the average weight of a 2207, and that's intentional.
Okay. So you've got it there at 34.4 grams.
Right. So it is not the lightest. There are lighter motors. But the weight's been chosen to be very similar to other 2207 motors.
So are you saying you could have done things to make it even lighter if you wanted to hit like 32 grams? But
yeah, absolutely.
That would have compromised durability?
No, it wouldn't necessarily compromise durability, but it would reduce performance.
I see.
And I think that we're comfortable in FPV with the weight of our motors in general. That's kind of the feedback that I got when I asked people. Yeah. And our frames are designed to handle motors of that weight. So having a motor that gives you, average performance at a lighter weight, maybe not so useful as having a motor that is no heavier than what you're currently flying, but delivers substantially more performance.
The argument is going to be that you're already flying a 34 or 35 gram motor. Why wouldn't you want to get the most performance and efficiency at no additional weight?
That's correct. Yeah.
Yeah. Okay.
That's the goal.
And the lighter motors aren't that much lighter. Like I see them coming down into like the 32 grams, which is 2 grams, 3 grams a motor, which is not nothing, especially at the end of the arm. But considering that you're getting, like, if I look at the F60 Pro, it's making max, where's the max thrust? F60 Pro, 1950
Pro,
kV, 16, let's say 1,700 grams of thrust roughly. And you're getting 200 grams.
Efficiency.
Yeah. You're getting 200 grams more thrust and slightly more efficiency for the exact same weight. Sounds like a good deal to me.
And the other big benefit that I've been able to realize with this is in responsiveness. Mm-hmm. So the bell of my motor, the Supernova, is a lot lighter than a typical bell, and that's from optimizing the thickness of the magnets and the thickness of the flux ring, which means that it's got the same torque, or actually more torque than a normal motor, but it has to accelerate significantly less weight, which means
so it's even more responsive.
Yeah, the responsiveness is, I mean, if you compare it again to the F60, let's say, similar kV,
right?
We got an RPM per second of 174,000, mm-hmm. and the AOS motor is closer to 200,000.
And that higher responsiveness is going to equate to better prop wash handling, easier PID tuning, and just better flying quadcopter overall.
Exactly. In fact, if we think of, like the sequence of delay that we have in our system, right, and trying to knock out the key sources of delay, the filters that we run on the gyro, mm-hmm. They add a few tens of milliseconds, maybe, mm-hmm. in the worst case, and or maybe 10 milliseconds or so. And then the next biggest source of latency in that loop from gyro to motor is how fast the motor can change RPMs.
Right.
Everything else, like the computation, everything is blisteringly fast.
Right.
But the motor has to physically change RPM.
Yeah. Yep. And a lot of people overlook that. We haven't really been able to measure the responsiveness of the motor on a real quad until bidirectional D-Shot was created. Mm-hmm. And as soon as people started measuring the actual responsiveness of the motor, I mean, it's on the order of 10 or 20 milliseconds between the time the flight controller commands the motor to change speed and the time the motor actually accelerates or decelerates to that speed. And that, that's substantial and has an effect on handling.
Yeah. And so the biggest thing we can do there is to make a motor that can change RPMs faster, mm-hmm. change thrust faster. And that, I believe, corresponds to what we need to make the quad fly smoothly.
Yeah, absolutely.
And this is something I wanted to maybe talk to you about. Like, I've been seeing a lot of marketing on motors talking about motors that are smooth, and motors that are smooth typically actually are less torquey. They use like N48 magnets or N40 magnets.
Absolutely. They use less powerful magnets. They have a larger air gap. And basically and sometimes they're lower kV is what I've observed. Yeah. And the net result is that a smooth freestyle motor is actually mostly just a less powerful motor. And that does kind of smooth it out in that it almost acts as a low pass because the motor's less responsive and less powerful.
Yeah, but that loss in responsiveness, I found, doesn't really lead to a smooth flying quad, because to combat prop wash and things like that, you need responsiveness. You need the motor to change RPM and the prop to change thrust really, really fast to compensate for those fast, turbulent effects in prop wash. And a smooth motor that is not very torquey and has a low KV just can't do that.
Okay, so we've spent this whole interview talking about how great your motors are. Now it's time for some harder questions that I wouldn't be doing my job if I didn't ask them.
Sure.
The first one is, how much is the motor going to cost?
So we're targeting a price of about $25 if you buy a set full.
Okay. So it's going to be on the, not like a budget $17, $18 motor. although arguably the fact that it can actually deliver numbers at the top of its class justifies the price. Speaking of those numbers, I trust you implicitly, but there are going to be people out there who say, oh, Chris Rosser made a motor and then he tested it and it was the best. Who could have predicted this? Is there going to be any independent verification of your numbers?
It's a good question. I don't have any problem with that. RC and Power are producing their own spec sheet for the motor as well.
They also manufacture the motor.
The manufacturer's numbers. They are producing their standard spec sheet.
Yeah.
For the motor as well.
I certainly don't want to put you on the spot here in the interview, but I think it certainly would add a lot of credibility and trust if we could find someone who does motor testing, who you feel you could trust their results and who is willing to do an independent test. If anything in that direction happens before the publishing of this video, I'll edit it in. And if not, well, we'll see how it plays out.
Yeah, maybe we could talk to Ryan Harrell and see if he would be interested.
That's who I was thinking of, but I didn't want to put you on the spot. He does great work. It would be cool to see him test them. Absolutely.
And I'm going to be hopefully able to send out samples and stuff for people to review and test out. But I really do believe in kind of what I've done with the product. So the more independent testing and verification of the performance, the better for me, because I really do believe it will perform really well.
The third thing that I've kind of had in the back of my mind is, and this is something people have questioned about your testing in the past, is like you love the RC and Power motors because they do amazing on your test stand, and that's true. But some of the people I've talked to, they say, yeah, I've flown those RC and Power motors. They're great right up until you get like one little rock in them, and then the air gap is so tight, or if you ding them a little bit, they're not as durable because they're very, very tight and precise. And so the question of durability, how are your motors going to be like very fragile?
I don't believe that they will be especially fragile. I'll give you the reason for that. One of the key areas where manufacturers before have tried to save weight is by thinning the flux ring. And the flux ring is like a big piece of machined steel that sits around the magnets.
Sure.
And steel is super durable. My motor has a thicker flux ring than typical motors.
Interesting.
So there is more steel in the bell and less fragile neodymium magnet than other motors of a similar type. In terms of materials, I mean, I think most top-end motor manufacturers are using 7000 series aluminium. RC and Power certainly do, and that's what this motor is going to be made from.
That's the harder, more durable alloy of aluminum.
Yeah.
Titanium shaft, I assume?
Yeah. Absolutely.
High-quality Japanese bearing?
Yeah, I mean, it's a motor. It's an RC and Power motor, so it's going to have all of the same features that you would expect and want from a premium motor that is designed to be a kind of top performer.
All right.
And in many ways, it's similar to. It's going to be similar to something like the Wasp Major or the GTS V4. Which is Minchin Kim's motor.
Right. What do you say to people who say, great, you've done these innovations, and now if they're actually good, everyone's going to copy them. We're going to see T-Motor's going to go, okay, we can do this. iFlight. Everybody's going to rip you off, man.
So I kind of have two views on that. The first is it's going to be not the easiest thing to copy this motor, because you change any of the parameters, you're going to move away from the optimum. So you'd have to be using exactly the same stator, exactly the same winding configuration, exactly the same magnets and all of that type of stuff. And unless people are going to go that extra mile to like precisely copy every single facet of the design, then I don't think it's going to quite be able to match the performance. So that's my first thing. I think unless you clone every aspect of it, you end up being slightly further away from the optimum.
It's not going to be like iFlight started putting a bushing on their bearing and everybody else went, oh, that's a good idea. And now everybody has a bushing on their bearing.
Yeah.
They may say, oh, we're going to put a thicker flux ring on. But unless they've actually done all the work, that's not going to produce the results that you're getting. That's what your argument is.
Yeah. There's a second way I'm looking at it, which is they are likely to copy some of the design ideas behind this motor, and that will make their motors better. And that's a good thing for the hobby and a good thing for FPV, and I'm kind of okay with that.
Awesome. So you haven't patented any of these design elements and try to prevent anybody from copying it, is what you're saying?
No, and honestly, it's not really patentable as far as I can tell, or at least it's not something that would be easy to patent. And if you could patent it, which I think is, I've written quite a lot of patents in my time, and I think that if you could patent it, it would be almost impossible to enforce.
Okay. Speaking of patents, you mentioned earlier in the video that you have another development. Before we move on to that, the motors are available to purchase now at the time that people are watching this, and links are in the video description.
They sure are, JB.
Okay. If people want to try these new motors for themselves, there's links down below, and I'm sure Chris would love to hear what you think of them. Okay. Anything more to say about that?
No. I guess there'll be affiliate links, and if you use them,
I damn well hope so.
And this channel, that's really good.
Yes. Okay. Chilling out of the way. What is this other new development that you actually did get a patent for?
Sure. So this is what I'm calling the X-cell technology. I filed the patent for this yesterday, so I can now talk about it and share it with you. I'm going to find the frame that has it.
What am I looking at, Chris?
You're looking at the base plate of a quadcopter frame.
Yeah.
And you're looking at 4 screws that go through that base plate.
Okay.
That mount a 30 by 30 stack. And the X-cell are the slots that you can see cut.
You've cut
around
slots around the mounting holes for the flight. This is a 7-inch. My scale is off.
This is a 10-inch.
This is a 10-inch. Okay. So that's a 30 millimeter flight control stack, and you've made these cutouts, and I assume that's to prevent vibrations from getting to the flight controller.
Absolutely right. Yeah, it's vibration isolation. And I have to give credit to Bob Rudy for this one, actually.
You do? Because
I came up with this idea very shortly after watching one of his videos where he was mounting like steel cable and things.
Oh yeah, I remember that.
Quads. You remember that video?
I do. Yeah. He was trying to do vibration isolation and using steel cables for vibration isolation.
Yeah, absolutely right. And trying to do vibration damping and stuff like that, and trying out a few different approaches. And I watched that video and I was really interested by what he was doing. And then shortly after that, I came up with this idea. And the goal for this technology is to connect rigidly the flight controller to the drone, such that the stack moves when the drone moves, because that's very important. We don't want to add delay.
Right.
But to disconnect the flight controller from areas of the frame that move a lot as a result of vibration.
That's interesting. You know what I'm thinking of? I'm thinking of there's a way that you can filter like sound waves by creating sound tubes of a certain size, and certain frequencies of sound wave will be blocked by the tube and other frequencies will pass through. And it feels like maybe like you're doing these cuts, and the cuts are leaving a little bridge, and that bridge is going to kind of filter out certain frequencies. Am I completely off base here?
You're kind of close. What you're thinking about
that's very generous of you.
What you're thinking about is traveling waves, right?
Okay.
Waves that move. Mm-hmm. When we're talking about quad vibrations, we're talking about standing waves. So waves that don't move.
Okay.
So what you have is and I might send you some B-roll you can cut in here, of a vibration mode where the arms of the quad are sort of bending up and down and vibrating. Some of my early videos, you'll have seen that happening where the whole quad's like flexing. Well, those movements of the arms cause the kind of base plate where the flight controller is mounted to flex and twist. And that transmits vibration to the gyro. Well, if you disconnect the flight control stack from the areas of the base plate that are moving as a result of that twist, and you only connect the flight controller stack to areas of the base plate that move the least.
Oh, I see. I see.
You are connecting the flight controller to quiet areas of the quad.
So this is not as simple as just take all flight control, all frames, and make these exact little curly cuts. You have to do a finite analysis of the frame, look at where it's twisting, and then find the points that twist the least and only connect it there.
Yeah, and disconnect it from everywhere else.
Wow.
And the result is you have a rigid connection of the flight controller to the drone. So unlike doing like a soft mount with rubber, you don't have any delay. You're not introducing any delay because this is a rigid connection.
That's what I was thinking of. You've got frames like the SpeedyBee Master, and they soft mount the entire flight control stack. And sometimes this works, but other times it just makes the whole quadcopter fly badly because of the additional delay. Anytime you're doing soft mounting, you're adding delay, and it can be a real problem.
Yeah, and also when you have a soft mount, because the soft mount is more flexible, sometimes you get more movement.
Exactly.
Not less.
Exactly.
As a result of vibration, which is also bad.
It has to be just the right stiffness to filter out the high frequency vibrations, but not be so loose that it's kind of flopping around. And they don't always get it right.
No,
and that's why.
And even further than that, it's sometimes not possible to get it right. So if you were to get the rigidity of the mount correct to filter out the high frequencies, it's soft enough that it now the stack has resonant vibration at a low frequency. So I have in the past played around with doing soft mounting and stuff for flight control stacks, and I came to the conclusion that it's wasn't a good idea. It didn't provide any benefit. But this isn't a soft mount. It's actually a rigid, hard connection. So you get no delay. You get all the benefit, but you get pretty extreme reduction in vibration. We're talking about on the order of 50%.
Well, I'm looking forward to the inevitable video that comes out on your channel showing the black box results and the gyro results and how much. This is especially a problem on big like Cinelifters, because the larger props have lower frequency vibrations and more powerful vibrations, and the cameras are extremely sensitive to jello. And so it seems like this is going to be a really big deal in the Cinelifter world potentially.
Potentially. And at the moment, I've got the design kind of nailed for flight controllers. So the first quads that will be coming out with this will be with a soft-mounted flight controller, or not soft-mounted, an XL flight controller with the isolation. And you just build your normal stack on top of that, exactly as you ordinarily would, with no difference. So they're pretty straightforward. But yeah, there is certainly some work to do to see if this can be applied to big camera kind of mounting plates.
Very cool. Well, appreciate you showing us that and look forward to see that come out. Chris, it has been great talking to you. It is always, I always feel like I come out of these conversations much smarter than I went in. And it's really great to see the work that you're doing to move FPV forward.
Thanks, JB. Yeah. It was really lovely talking to you as well, and I'm glad that I could share this with you and everyone else as well. Yeah. All right. Cool. Well, I can't wait till the next time. If you guys are interested in seeing more of Chris Rosser talking about motors, I'm going to put a couple videos on screen because this is not the first time we've come together to talk about motors.
I don't know what videos those are going to be, but I'm going to put cards on screen and links in the video description below, and you can be assured that they are just as interesting and educational as this one was. We will see you there.